Hello all, I'm J.R. Sophia, Assistant Professor of Physics. In the previous video, we have understood what is a tensor and the occurrence of tensors in various physics concepts. In this video, we are going to understand notations and conventions involved in tensors. Notations and convention. Consider an n-dimensional space and x1, x2, xn are the set of coordinates in that space. For reference, we have a three-dimensional space which includes x, y, and z as the coordinates. It means if we have an n-dimensional space, we have n coordinates. Very much like that. We have a three-dimensional space, so we have three coordinates x, y, and z. Here, the terms 1, 2, and n on the power of x doesn't mean that it is ith power of x. It merely means it is a superscript on x. It is just a notation, not the ith power of x. The n-dimensional space, it can be denoted by Vn. Let us say I have a function which is a function f which is going to be it is variable. It depends on variability. Then we can very much write f of t. Let us say I have another set of coordinates very much similar to we have x, y, and z as the coordinates. Let us arguably say there is x bar, y bar, and z bar, which are also going to be coordinates in our three-dimensional space. Then we can write it as a general notation x bar alpha because we can write x bar 1, x bar 2, x bar n, which is also existing in the same space Vn. If that is the case, we can use this notation x bar alpha to say this is the conventional set of coordinates and this is the new set of coordinates. This is the common notation x bar alpha. Clearly, each of the coordinates xi will be a function of n coordinates x bar alpha. What do we mean by here is, so let us say I have a new coordinate x bar. I want this x bar to be a function of x, comma, y, comma, z because I want this to be a function of the older coordinates. As well as I want the older coordinates to be written in the form of it is x bar and y bar and z bar. That is, new coordinates can also be rewritten in terms of the old coordinates can also be written in terms of the new coordinates. This is in short can be written this way. The old coordinates xi are now can be functions of x1 and x1 bar, x2 bar, x3 bar, and so forth. And the new set of coordinates x bar alpha, they are going to be functions of x1, x2, x3. Here, why do we write alpha and I is that it is to say I can vary from 1 to n. So x1 is a function of all these barred coordinates. x2 again is a function of all the barred coordinates. And x3 and it ends up in n. Very similarly, here alpha it is lying between 1 to n, meaning x bar 1 it is a function of x1, x2, xn, and x bar 2 is also going to be function of x1, x2, x3, and xn. That is why we have written this way. Example 1. Express the Cartesian and spherical polar coordinates as a functions of each other. Now we have reached a point where there are two set of coordinates, very much similar to this concept where x1, x2, xn are one set of coordinates and x bar alpha, which is like x bar 1, x bar 2, x bar n are the new set of coordinates. Very similarly, we have Cartesian coordinates, which are the older ones, and the spherical polar coordinates, which are the newer ones. Let us first understand what is this new coordinates r, theta, and phi. We know what is x, what is y, and what is z. Let us understand this is point P, which is arbitrarily occurring in a three-dimensional space. And we are going to draw a line between the origin and this point P. The line, the magnitude of this line, the length of this line, it is going to be given by new term called R. This is the first new coordinate. What is theta? Theta is going to be the polar angle. That is the angle, this R, it is going to make with the z-axis. That is the angle theta. What is phi? Phi, it is, you have to project this R onto this space xy plane and you have this projection. This projection It creates an angle phi with the x-axis. This is the third coordinate phi. These are the spherical polar coordinates. The coordinates x, y, z, they are independent of each other. Very similarly, r, theta, and phi are also independent of each other. Now we want to write one set of coordinates as a function of the other set of coordinates. The Cartesian coordinates are related to the spherical polar coordinates by these equations. How come? We know this is r. If this is theta, the side which is opposite to theta is going to be r sine theta. This is also r sine theta. This is also r sine theta. If this is phi, this side is going to be sine phi. Uh, sorry, r sine theta sine phi. This is because this is the hypotenuse, so this is going to be r sine theta sine phi. Very similarly, this side, which is going to be the adjacent of this angle phi, it can be written as r sine theta cos phi. This is going to be r sine theta cos phi, which is the which is the x coordinate, or this is going to be my x. So x is going to be replaced by r sine theta cos phi, and this is actually my y component, and this y is replaced by r sine theta sine phi, and this is my z component. Z can be replaced by, or this is if this is r, this is theta, and z is actually lying adjacent to theta. So z is written as r cos theta. So with that in mind, we can write these three equations. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. What have we done? We have done the older coordinates are written in terms of the newer coordinates. And the inverse transformation. What do I want? I want the newer coordinates to be written in terms of the older coordinates. How do we do it? Very similarly, we have r, theta, and phi marked. What is this actually? I want this r. This is actually made of this, and this is a triangle which has sides, this and that. And what is this actually? This is actually made of these two. This is the hypotenuse. So this is my x, this is my y. So this is going to be root of x square plus y square whole power 1 by 2. If this is going to be x square plus y square whole power 1 by 2, plus this is going to be z, then this is nothing but the hypotenuse r, which is written in the form of x square plus y square plus z square whole power 1 by 2. Now, what do I want? Theta. Theta can be attained by finding out tan theta. What is tan theta? Opposite by hypotenuse. So, opposite side is actually this x square plus y square whole power 1 by 2 divided by the hypotenuse. What is the hypotenuse? It is the z value. So, theta is going to be tan inverse of this. I want this phi to be written in terms of old coordinates x, y, and z. This is very similar to this. We are going to find tan phi. Tan phi is equal to opposite by adjacent. So it is going to be y by x. Tan inverse of y by x is going to give me phi. That is, the newer coordinates r, theta, and phi are now written in terms of the older coordinates. So we have attained the first transformations. That is, we have transformed the Cartesian coordinate system coordinates into spherical polar coordinates and vice versa. So coming into we are now going into the Einstein summation convention. Let us say I have the older coordinates xi in terms of my newer coordinates and newer coordinates in terms of my older coordinates. Let us do differentiation on equation 3. What do we have? We do not know how do we write this straight away. So let us take the known thing. X is equal to r sin theta cos phi. That is what we already know. If I have to differentiate dx, then I know that this is comprising of three parameters r, theta, and phi. So this is going to be partial derivative dou x by dou r with dr. And dou x, it is a function of theta also. So dou x by dou theta times d theta plus dou x by dou phi times d phi. So we understood the older coordinate dxi. It is going to have a summation involved. older coordinates on the top, newer coordinates on the bottom, and followed by dx of d of new coordinates. So this way we have written this notation. So dxi instead of the older coordinates, you have this, and you have a dou by dou r, which is the older coordinate, newer coordinate. So dou xi by dou x alpha, and followed by there is a d new coordinate. So d x bar alpha. Now, as there is a summation go summation, we have three coordinates, so we have summation over three. I mean, the alpha, it is going to vary because this is the new coordinate system which is varying here. So alpha varies from 1 to n. This way we have written this. This is written, this is going to be 6a. The inverse, if you think of this, then what we have is r is equal to x square plus y square plus z square whole power 1 by 2. If I want to find dr, we know r is a function of x, y, z. So for obvious reasons, we'll write dr is dou r by dou x into dx, dou r by dou y into dy, plus dou r by dou z into dz. In this way, we'll write it as a notation which involves the new coordinate on the left. So dx bar alpha. Similarly, the new coordinate on the top, so dou x bar alpha divided by the older coordinates dou xi, followed by d older coordinates, so dxi here. Summation is involved. We know x, y, z. So the older coordinates only vary. So the summation is happening in terms of I, because I varies from 1 to n. If we have three coordinates, so the summation involves three terms. So if we have n coordinates, then you have to have summation over n terms. So we are taking this equation and we have written in this form, which is actually, this is equation 6b. Einstein summation convention says that if we have repeating indices, let us say in the right hand side of 6a and 6b, we see alpha repeats itself here, I repeats itself here. So if we have repeating indices, then it already means that summation is happening for this indices for n times. If there are n terms, it is going to happen n times. N terms are going to get summed up. This is the Einstein summation convention. So we can drop these summation terms involved because it's subconscious. It is saying that the summation is going to happen for alpha 1 to n, as alpha is repeated here. I is repeated here. So it says summation happens from I starting from 1 to n. So we drop the summation terms involved. This is the Einstein summation convention. Equation 7a and 7b, alpha repeats itself. So that is the case. Now we are going to know what is a free index. What is a free index? If an index appears only once in a term, it has a definite value, any value between 1 to n. Such an index is called free index. For reference, let us take 7a. Here, I stands only one times on the right hand side, whereas alpha repeats itself. So I is unique one. So this index which is going to occur independently, we can call it as a free index. Free index in both these equations 6a and 7a, you see alpha as the repeating one, so I is the free index. In equation 6b and 7b, alpha is the unique one, so alpha is the free index here. That is what you have written. 6a and 6b is 6a and 7a, I is a free index. 6b and 7b, alpha is the free index. Also, here we have used this alpha varies from 1 to n and I varies from 1 to n. That can also be dropped and we can write this way. What now we'll understand dummy index. What is a dummy index? Any index is repeated over one more than once, then we can call it as a dummy index. For obviously alpha repeats here, so alpha is dummy index here. I repeats here, so I is the dummy index here. Example 2. Let us say I have four different coordinates. That is very similar to xi, yi, zi. So A varies from A1, A2, and AN. B will start from 1 to n, B1, B2, Bn, and so forth. Now we have to understand the conventions which are involved in if we have a four set of coordinates, four set of n quantities. So what do we mean by AI, BI? It means both these indices are going to be the same, 1, 1, 2, 2, n. So what do we mean by A, I, B, J, C, J? We mean that this is the free index. These are going to be the dummy index. That is AI remains, but this will vary 1, 1, 2, 2, so forth and. Because I is a free index, the other one is not a free index. If we write AI, BI, it means that we say these two are going to be free indices. So they can vary. J, A, AJ, BJ, AK, BK, and so forth. If AI BJCJ means this is free index, so AI repeats itself, whereas the dummy index can vary together. These are the known thing. First observation or first uh, thing we are trying to prove is that AI BJCJ is not equal to AI BICI. What we say here is if we have one dummy index over here and one free index and two dummy indexes over here, then we cannot say this is going to be equal to all the three indices are going to be same free index, all the three coordinates of the free index. Let us verify by equation 2, where we have written this way. AI BJCJ means AI is retained, whereas the other two terms vary. So AI BJCJ can be written as AI B1 C1, AI B2 C2 and so forth. Whereas AI BICA means all the three terms are going to vary simultaneously. So looking at these two equations, the expansion, we can surely say that AI BJCJ can never be equal to AI BICA. The second thing we are trying to prove is AIBI CIDI is not equal to, if we have like two free indices in this way, then this is not equal to that. What is this expansion? It means that all the four indices for the four coordinate system are going to be varying simultaneously. A1, B1, C1, D1, A2, B2, C2, D2, and so forth, ends up in A and B and C and D. But on the right hand side, what we say is these two are going to be varying independently. Whether this will vary independently. These two are not in. There is no connection between these two indices for these particular coordinates. So this it means that you're going to summing is happening over I. Here summing is going to happen for J. So if we expand this, it is going to be A1 B1, A2 B2, ends up in A and Bn. And this is going to be C1 D1, C2 D2, and C and Dn. And if we try to get the products here only the A1, B1, C1, D1, and all these terms only remains on the right hand side. But whereas in this term, there are this A1, B1, C1, D1 terms, original terms, along with the cross terms, which is A1, B1, C2, D2, and all these cross terms are involved, which are not occurring in this equation 6. So from these two equations, we can say this is not going to be equal to that.